In today's lesson, we are going to try to connect the dots. We talked about electron pair domains and hybridization in Lesson 2, and the Lewis octet in Lesson 3. What the missing dot is represented by is the valence shell electron pair repulsion theory. And what this theory will allow us to do, when combined with these other three topics, is allow us to interpret the three-dimensional nature of an organic molecule. So far, we have learned that a molecule's Lewis structure will allow us to determine the number of electron pair domains that surround a given atom within that molecule. And by counting the number of electron pair domains around each atom, we can derive each atom's hybridization as well. One aspect we have not covered, however, involving counting the number of electron pair domains around a given atom, is that by counting the number of electron pair domains, we can predict a molecule's three-dimensional geometry. The Vesper Theory is a model that we can use to predict the way electron pair domains will orientate themselves within space, and an understanding of this model can come by looking at its name. Basically, electron pairs are negatively charged and will repel away from each other. Hence, the valence electrons that surround an atom will move as far away from one another as possible, as long as the octet rule is still satisfied for that atom and the number of electron pair domains is maintained. The carbon atom of carbon dioxide has two electron pair domains and is therefore sp hybridized. We could see that the two electron pair domains are these two double bonds that surround carbon, and remember, each double bond consists of one sigma bond and one pi bond. Now let's take a look at the three-dimensional model of carbon dioxide. What we can notice is that the carbon and the two oxygen atoms are located in a single plane and indeed exist in basically a linear line. This is due to the Vesper theory and the two pi bonds surrounding that carbon atom repelling as far away from one another as possible. As an additional note, remember, each carbon atom is composed of one sigma bond and one pi bond. If we take a look at the electron density for where the electrons of that sigma bond are located in space, we could see that they lie within the same plane that those atoms are in. However, if we take a look at the electron density met for the pi electrons of each double bond in carbon dioxide, which are represented by the big red and blue lobes, we can see that the pi electrons lie outside the plane that each of the atoms and sigma bonds are in. This is the case with all pi bonds, and a concept that we will learn more about when we study hybrid molecular orbitals in lessons 10 and 11. If we take a look at the carbon atom of acetic acid, what we'll notice is that it has three electron pair domains and therefore is sp2 hybridized. If an atom has three electron pair domains and is sp2 hybridized, we will consider it to be trigonal planar. If we take a look at the three-dimensional structure for acetic acid and focus our attention to that carbon atom that has three electron pair domains, we'll notice that the three electron pair domains forces the three adjacent atoms attached to that carbon atom to lie in the exact same plane, hence the name trigonal planar. But what about the case when an atom has four electron pair domains? How can we use the Vesper model to predict the orientation of each of these electron pair domains in space about that atom? While this is probably the toughest example to visualize on paper, it becomes a bit easier if we consider a playing jack. Does the Lewis structure below correctly represent the three-dimensional geometry of this carbon compound? And the answer is no. Organic chemistry is a three-dimensional subject trapped in a two-dimensional world. So how then can we indicate this three-dimensional geometry when confined to a two-dimensional sheet of paper? And the answer comes that we will use wedged and dashed bonds to represent these molecules in three-dimensional space. What we can notice by taking a look at the three-dimensional model for this molecule is that the fluorine atom is directly in front of the bromine atom. How did I know which atom is which? Well, if I hover over that atom, I could see that it says F4, F for fluorine. But another way to determine which atom is which is by using the periodic trends that we studied in Lesson 1. Remember, atomic radii increases as we move down in the periodic table, and since fluorine is above chlorine, which in turn is above bromine, that means bromine will be the largest while fluorine will be the smallest. It is important to note that when we look at the three-dimensional structure of this molecule, that the fluorine is directly in front of the bromine atom, whereas if we look at the Lewis structure for this, the fluorine is indicated by a wedge, which tells us it's coming out towards us. But notice that that wedged bond for the fluorine is aligned to the right, and the dashed bond, which indicates the bromine is going back, is aligned to the left, when in reality, the fluorine is directly in front of that bromine atom. For a lesson summary, we learned that the Lewis structure of a molecule allows us to count the number of electron pair domains that atom has, and by counting the number of electron pair domains, we can determine the geometry of a molecule as well.